Hi everyone, my name is Miriam, and in this presentation we will continue on the topic of response adaptive randomization, also known as RAR. At first I wanted to give you guys just a quick overall view of response adaptive randomization. As you can see in this graph, the top one is the traditional fixed sample design, which is you design the study, you conduct a trial, and then you analyze the data. However, in the adaptive design, same thing, you design a study. As you conduct the trials, you will review some of the outcome, and if adaptive randomization is needed, you'll make those changes, and then you continue conducting the study and analyzing the data at the end. So here I wanted to go over some of the pre-planned changes that an adaptive design may permit. Just keep in mind they're not just limited to the following criteria, but I just wanted to go over some of those adaptive design with you guys today. So the first one is refining the sample size. Second one is abandoning treatment or doses. Third one in changing the allocation ratio of patients to trial arms. Fourth one is identifying patients most likely to benefit and focusing recruitment efforts on them. And the last one is stopping the whole trial at an early stage for success or lack of efficacy. What are some of the methods that are used to extract data? So in an adaptive randomization, either frequentist or Bayesian approach can be used to extract information from the accumulating data. For example, if at some point of the trial 50 and 40 patients have been enrolled in 2 treatment arms, and 16 and 10 successes have been observed, a frequentist would compare the point estimates, which is 16 divided by 50, which is 0.32, and 10 divided by 40, that's equals to 0.25. And then determine the allocation probability to the first treatment by dividing the first one, which is 0.32, divided by total, which is adding up the 0.32 plus 0.25. However, in the Bayesian, instead we would determine the allocation probability by the posterior probability, P1 greater than P2 in our data. And P1 and P2 are the success probabilities of the 2 treatments. How does the RAR procedure work? So suppose you have 2 treatments under one study, and theta is an unknown parameters from the employed model. Rho of 1 of theta is the theoretically optimal allocation proportions for the treatment. First, we assign the first 2 times N0 patients to 2 treatments by some restricted randomization procedures. We can use permuted block randomization, for example. And then second, when the alpha of 1, the L greater than 2 times N0, which was our patients that were assigned, let me go back to the 2 treatment arms, arrives, we obtain the parameter estimator, which is ith of L minus 1. And the estimated optimal allocation proportion, which is rho of 1, and then you subtract the 1 from this 2. I just wanted to go back and show you guys that rho of 1 of theta is the theoretically optimal allocation proportion for the treatment. Based on the previous, on all the previous treatment assignment and responses. Third one, we assign the health patient to treatment 1 with the following formula to calculate probabilities. And then where the n in the previous formula, the n1 of L minus 1 is the actual number of patients in the treatment 1 after the 1 is subtracted from L patients. And as you can see in the formula, this is the allocation function satisfying when you give the treatment group of 1 and 0, and this formula is used to actually calculate that probability. So from the previous formula, we can easily see that every treatment assignment depends on the previous responses and assignment. So you go back 1 and look at the responses and then make your decision based on that. So everything depends on what the outcome of the previous assignment or response has been defined. Therefore, it is desirable to drive the asymptomatic properties about parameter estimator as well as the allocation proportions. Hu and his colleagues studied offers the asymptomatic normality for the parameter estimators following general response adaptive randomization designs with convergent allocation proportions. So to continue this, the sequential monitoring is a standard in clinical trials. Therefore, it is worth investigating how to perform statistical inference when sequentially monitoring a clinical trial using the response adaptive randomization designs. The primary task of sequential monitoring is the control of the type 1 error rate, and the key is to obtain the joint distribution of the sequential statistics. In practice, it is not always practical to obtain immediate response. Logistically, delayed responses will not bring about trouble for implementing response adaptive randomization design. Since we can update parameter estimators, an allocation probability function would observe responses instead of all the responses from the enrolled patients. However, it was unclear how delayed responses may affect statistical inferences in clinical trials. So Schmidt thesis was done on a more general adaptive class of GSTs, which was covered in the lecture. I wanted to go over this one a little bit with you guys because I found it pretty interesting and might be useful for this lecture. So the first step was to sample size, specify the group size, then decide whether to continue or stop. The second stage is to choose group sizes and stopping boundary values. Then sample size, the second stage again, specify the group size, then decide whether to continue or stop. For the third stage, choose group sizes and stopping boundary values. But this is only done for adaptive designs. So you initially choose an N1 and continuation interval C1, which is between those boundary of A1 and B1. Then observe the Z1, which should be part of the Z1, and then choose your N2, which is N2 of Z1. And then continuation interval for C2 of Z1, which should have the boundaries, and observe this Z2 and go ahead and continue with that until you have determined to stop at some stage. So there should be a fixed K that In that stage, you will stop the continuation of that interval. Could be 5 or a 6 or any other fixed case. Here in above formula, Z1, Z2 are the usual Z statistics based on accumulating data. But we need to specify design and decision variables. So as we choose the N1, the boundaries, all of them, and the fixed K has to be specified in order for your design to stop at some point of time. There are a lot of these variables. They must be specified so that the stated type 1 error constraint and power requirement are actually satisfied in this study. In addition, we would like to produce to be efficient in some senses. Lastly, I wanted to go over some key points with you guys. First one is design a strategy of multi-stage plan in order to achieve a smaller effect size. However, it is recommended to have an aggressive early stopping boundaries. In addition, allowing adaptive group sample sizes appears to add only a little benefit in the efficiency of your study. Second one is that it has been known that most adaptive designs that have been proposed in the literature are much worse, mainly due to using non-sufficient statistics and use of ad hoc arbitrary sample size increased rules. In addition, one of the useful tools to respond to truly unexpected circumstances is via adaptive designs using combination tests. However, they should not be applied to as a substitute for poor or delayed initial planning. Thank you very much for listening to this lecture today.